So let's start by talking about linear models and their hypothesis space. Recall in Lecture 1 we introduced script H, which stands for the hypothesis space of a model. It represents the universe of possible hypotheses that a certain learning algorithm can generate. When we think about linear models, we can think about what types of choices or parameters that we are going to change in order to get a different hypothesis. We're going to call these parameters theta, which we talked about before. And given these choices of thetas, what types of boundaries can it generate? Let's look at this diagram from Wikipedia, which is their notation for any type of machine learning article. It's sort of instructive here. We're not going to go over it in detail. We'll go over it later when we cover support vector machines, which is a type of analogizer. But for now, let's just look at diagram A and B. Okay, it's quite clear that if we have a linear algorithm, which just represents a linear combination of the input values, each independent feature value, we won't be able to generate a decision boundary like A. So that's out of the question. But we will be able to generate something like B because it's a hyperplane in one dimension, right? Just a line in this 2D surface. We can say that linear classifiers represent a simple hypothesis set because we can only create straight lines or hyperplanes with a linear classifier. In other words, we cannot create any curved or dimpled surfaces as a decision boundary, unlike those that you saw with K and N. Even with this restriction, we can simply see that the hypothesis set of linear classifiers is in fact infinite in size because we can draw any number of lines with different slopes and choose different intercepts. We're going to learn today about a simple algorithm called Perceptron, which allows us to capture the notion of a linear classifier. Let's go back again and think about the credit card application process in which a customer creates a credit card application for submission to a bank. In this case, we might get inputs such as their age, salary, or even number of years in current residence. All of these can be changed into a numeric form, and then we can create a scaled version of these features by multiplying each of these xi inputs against a corresponding theta I. We're going to take those product terms that you see here, sum them all together to get a score. And this score, if it exceeds a certain threshold, we're going to say that the credit card application represents a customer that is good enough to be approved. In other words, it won't lose the bank money. And if the score does not meet the threshold, we're going to deny the credit card application. So we can think about this as a credit score. This linear formula is just one of many different formulas that could have arisen from the entire hypothesis set script H. But through the search for a particular set of coefficients, theta, we have decided on a particular hypothesis. We're going to call that H of theta, and it has this formulation, right? What we're going to do is we're going to take the threshold that you see here, and just move it back into the formula, and we'll get this particular version of it, where the signal, which is in this part, has the threshold minused off of it, and then the sign will just give us the classification. Positive if we are going to approve credit, and negative if we're going to deny it. We can do additional simplification. We can take the threshold and the negative of it and change that into a parameter as well. We are going to call this the bias weight, or theta 0. We're going to substitute the negative of the threshold and call that theta 0. With this, we can introduce an artificial coordinate x0, 1, and then it becomes very compact and simple to represent because we're just going to change the index from 1 to 0. In vector form, the perceptron implements this particular equation, right? Just a sign of the vector of weights, theta. We transpose it so that we can multiply it against the vector of the instance, x. And then we're going to get a decision boundary that looks like this. This is a case of a 2D problem where we only have x1 and x2. The perceptron algorithm implements a learning algorithm based on the signal, which is theta t times x. This is the vector multiplication of the weight vector times the input vector, both of size n. We're going to take the sign of that output and say it's going to be a positive instance if the sign is positive and a negative instance otherwise. Now we want to cover how we're going to do the steps within the perceptron learning algorithm. First, we're going to initialize the weight vector theta in any fashion that we'd like. We could assign it all zeros or assign it some random numbers, such that we fill up all of the n entries. Then we're going to look at the training set and iterate. Every time we look at the training set, we're going to pick one of the m examples that we know we're not currently getting correct. We're going to look at that misclassified point, which is easy to identify because it satisfies this equation, right? The sign of the output of the classifier, which will be +1 or -1, won't match the intended target value. So when this criteria is satisfied, that becomes a misclassified point. After that, we need to update the weight vector to try to get this point correct. How do we do that? We're going to update the weight vector from the original amount by adding a term that is just based on the current misclassified example times its actual class. When we add these two terms together, we're going to get a new weight vector theta prime. The key part of the perceptron learning algorithm is understanding what this term is doing. And to understand that, we've drawn the diagrams on the right, but it probably helps to walk through this in a bit more detail. Let's make some assumptions to help us work through this. Let's first assume that yi, which is the misclassified example's label, is actually supposed to be positive. Let's also think that all of our xi's are positive values. Let's go ahead and plot this out. So I'm going to draw a two-dimensional axis with the origin here. Since our xi is positive, it's going to land in the upper right quadrant somewhere. Let's say it looks like this. It's just a bunch of coordinates that are all positive, so we can write it out as a positive vector. And because our current weight vector, when multiplied against this vector, becomes a negative number, our theta must be pointing in a negative direction. Given this, what we'd like to do is update the weight vector so it starts to classify this instance more appropriately. That can only be done if the weight vector theta crosses over to the positive space. Let's look at the term that we're going to add to it. The term that we're going to add to it is this multiplication of yi xi. It's going to point in the same direction as xi because it's just simply a scaling factor. Remember, yi is just a scalar that's being multiplied. In here, this case, it's a +1. So we're going to get a +1 multiple of xi, and it's going to help us move theta coefficient over. And now we can see that we can appropriately classify this example because now the multiplication of theta prime times xi will give us a positive value. Now let's go look at the negative example. Here we're going to say that yi, the misclassified example was actually supposed to be negative. We're still going to maintain, for ease of exposition, that xi is of some positive value. Let's go out and plot all of this on our xy plane. We'll have the origin here. And because xi is positive, it's going to land in the upper right quadrant. Since the weight vector gets this classification wrong, this means that theta must actually be pointing in the upper right quadrant. What we'd like to do is push theta prime, the updated theta, to classify this particular vector negatively. So we have to get the weight vector into the negative quadrant. yi times xi here is going to be a negative value because it is a negative example and the input vector is all positive. And it will be parallel to xi, just reflected in the opposite direction. Thus, our updated theta prime now points in the negative direction. And we'll get this particular training example right after the correction. You can see all of this on the slide here. But do take some time to review this because this is a key part of the algorithm that's a little bit difficult to comprehend. In particular, try to examine the cases where the input vector is not all positive. To sum up, PLA executes learning by doing an iterative process where it updates its weight vector from theta to theta prime by looking at a misclassified example and then picking that misclassified example and then updating the weight by taking the input vector and timesing it by its actual classification. This is going to help the weight vector update in such a way that it will try to classify the misclassified training example to the correct one. As you can see on the right, this basically takes the weight vector, which might not get a particular example right, and try to force it so that it will become part of the correct examples. So how does PLA work? At the beginning, we have an initialized weight vector, for example, all zeros, which classifies everything the same way. I'm going to pick a misclassified example, this red cross here. After updating the weight vector has moved from classifying everything as red stars and making a border where the pink area is for the blue circles. We identify another misclassified example, this time the cross in the upper right, and we're going to update the weight vector accordingly. By updating the weight vector, sometimes we can make a lot of errors at once. Here, after updating the weight vector in iteration 2, we've misclassified a lot of blue circles, so the error rate has gone up a lot. We're going to select another blue circle and iterate again. That still improves the process, but we still have some misclassified examples which you're going to select, and finally arrive at a good setting. I should just clarify, this one is supposed to be on the wrong side of the classification border, so it should be a little bit over here. As you're paying attention, you might have noticed that PLA doesn't seem to always work. There were some steps in which, by correcting a misclassification, we got other examples that were already classified as correct and made them incorrect. That can happen quite a lot in PLA. So you might be wondering whether it actually converges. In fact, we'll try to show this in our post-lecture videos, but we'll introduce the theorem for now. If the data can be fit by a linear separator, then after some finite number of steps, PLA will eventually find a linear boundary that correctly classifies all of the examples in this binary classification task. But what happens if we give a data set that's not linearly separable? What happens then? Now it's your turn to think about what might happen in this case. In summary, we've learned PLA, which is the perceptron learning algorithm. It's one of many iterative learning algorithms that you're going to be learning throughout the course. In its vanilla guise, it is a binary classification algorithm. And like a lot of other linear classifier, it uses the signal of the weight vector taking the product with the input vector. We can start it with any type of weight vector we want, for example, a zero weight vector. And every time we go through an iteration, we identify an error and try to correct it by nudging the weight vector theta in the correct direction to get that individual example correct. And it will converge given sufficient number of iterations if the data is actually linear separable.